infinity means there exists a coding, converse means there is no coding. And actually this channel capacity can be proven mathematically. But we are not going to cover that in this particular lecture because that will take another hour to do so. If you are interested, you can have a look at these list textbooks. I recommend these, especially because they are quite easy to follow. Is this up? I think 10 quarters of step. Okay, this is the summary of the proof step. If you are interested, I recommend you to have a look at this. Yeah, so I mentioned earlier on about the channel with memory. So in literature, the channel capacity has been extended to the case of memory. So this is the definition. So you have to take it instead of a symbol wise, you have to take it code word wise. And what makes it difficult is this optimization and this limit towards infinity. So I can say confidently that for most of the cases, this expression is still an open problem. No one has been able to find, for example, the capacity of wireless channels with memory. The capacity. The capacity. They can find the bounds, upper and lower bounds, but not the capacity. Okay. It's an open problem. There are a lot of rooms for the work. But obviously the problem is it's not very easy from the perspective of this. Okay, so from this review, we'll proceed to the second part, which is basically the main area of today's lecture, the main topic of today's lecture, on the deterministic MIMO capacity and multiplexing capacity. So by deterministic, I would like to clarify that this represents a MIMO channel where the channel stays constant. They are not changing over time, so there is no randomness involved in the case of the MIMO channel. So 2x2 MIMO channels, we have two antennas, 1 and 2 at the transmitter, and two antennas at the receiver. And with these two antennas, we can have 4 possible transmissions, right? And then we can write this model. So y is equal to hx plus z. And then we have h1, h2, x plus z. So y in this case is a vector, right? y1, y2. Y is a the signals at the receive antenna. So it's a vector. H is a metric, so 1, 1. 2, 1, 2. So this is H. X is also a vector of 2 because we have 2 transmit antennas. And Z is also 2 because we have 2 receive antennas. So Z usually relate to the noise generated at the receiver. So we can write this down as y equal to h1. So what is h1? H1 is actually this column. x1 plus so this representation is related to this particular vector. So the reason why sometimes we write into this is we want to identify the symbols emitted from each of the individual transmit antennas.
About the deterministic itself, this is only, we are talking about H1 and H2?
Yes.
Not the AWG and
No. Okay. So, just to clarify that the deterministic is constant with H, because H is the MIMO channel matrix. So the AWGN itself is clear, because otherwise the analysis will not make sense, or we can stop at this point and leave the class after that. Okay, so what's interesting about the MIMO is there is a possibility that H1, so H1 is like the transmit factor from antenna 1, so this is H1, these two sort of transmissions. H2 is the vector generated from the antenna 2, so it's actually that vector. So if H1 and H2 are not in the same directions, then we can transmit two independent symbols from these two transmissions. So this is the pictorial representation. So if H2 and H1 they are not related at all, or they have been related with with little alignment, then we can transmit the impedance symbol across these two vectors. So sometimes H2 can be like this line, So in this particular case, H2 is not very useful because we cannot transmit two independent symbols across H1 and H2. So the way the MIMO works is because of this possibility of having channel vectors that are not line, So we can transmit independent symbols across these two vectors. So we say in that particular case we have 2 degrees of freedom per channel use because we have 2 possibilities to transmit 2 independent symbols. And then we can also say that the multiplexing gain of 2 with respect to the single input, single output channel. So what about if we generalize that into NT times NR MIMO channels? How much degree of freedom that we can expect from this channel? Any guess?
T.
Sorry?
T.
T? What is T?
Number of
Oh, NT. NT.
The smaller one between NT and NR.
Yeah, so that's smaller number between. So it's actually related to the rank of the H of the MIMO channel matrix H. We will come to that in a few seconds. Okay, so this is the assumption, so it's a bit more detailed. So suppose that input X is a vector, anti-dimensional vector. Because it's anti-dimensional vector, the property is on the covariance matrix. So you have the covariance of X is equal to the E. So if you see this E, these are expectations, or mean, or average, equal to, we divide it as Q. And then we have the output Y, which is the NR dimensional vector. We have noise Z is NR dimensional AWGN vector. This is the assumption. So IID Gaussians. Gaussian is normal distributions with 0 mean and variance and null. Standard AWGN assumptions. So the covariance matrix for that is the scale identity matrix. And then the noise is ID over all time instants. So the fading edge is NR times NT. So this row determines the number of receive antenna. This column determines the number of transmit antenna. Okay, so what we assume also is the input X and the noise are independent, which is acceptable assumption as far as most of the communication systems are concerned. Is there any case where input X and Z are not independent? So somehow the input X affects the noise. At first I didn't think that it exists, but it does happen, especially in the case where we are dealing on we are dealing with the communications channel that exists in the integrated circuits chips, because the moment you generate the data, that will generate heat, right? And remember that the EWGN channel is very sensitive with the thermal property of the environment. So the data being generated is actually increase the level of noise, and that actually make that the input and the noise are not totally dependent.
So this means that the noise value is somehow dependent on the value of the X.
Yes. On the power being generated by having X. So if you have that particular setup, then you have to start the analysis of the capacity from scratch, because then we cannot use Shannon, the Shannon famous formula of log to 1 plus x. All the assumptions will be here. Okay, so this is just some pictorial representations of the model. So I just say here that the column T of H indicates the fading factor from transmit antenna T. Row R of H indicates the fading factor for receive antenna R. So sometimes, this is just my personal experience, sometimes when we read this kind of statement in the paper, it's hard to follow, right? Sometimes. So I think the best way to try to digest this information is just to draw the factor and the matrix, and then we can identify what does it mean by the factor from transmit antenna T and factor for the receive antenna R. Okay, using the definitions of the mutual information, because we want to find the capacity expressions. So the mutual information between X and Y is given by the difference of the two entropies, HY minus HY given X, and equal to HY minus, what is Y here? Y is HX plus Z. So we know that H here is deterministic, so it does not affect the uncertainty. X here, since it's given by X, so this is also deterministic. And the overall entropy is only governed by the entropy of Z, of the vector Z. So we know Z, so what is Z is complex and it should be an R. It's not NT, yeah? It's an R. So complex NR variate normal distributions or Gaussian distributions, from which the entropy is given by this log 2 determinant of E covariance of C. If you want, you can do this calculation manually, but obviously this result is well established, so you can simply use this result and do more calculations. Okay, so we can find the entropy of Z here. We need to find the entropy of Y. So we know the distribution of Y. We know that H is deterministic. We do not know the distribution of X. So obviously in this case we cannot fully evaluate the entropy of Y. So we need the distribution of X in order to evaluate the entropy of Y. And if you are lucky, if the distribution of X is optimal, then maximizing the mutual informations will give us the channel capacity. So if you are lucky.